Okay, hello, nice. My name is Kazuki from AIST Japan. Um, Actually, I'm a researcher at the Japanese Institute, National Institute of Advanced Industrial Science and Technology. It's so long, and we just call it AIST. This doesn't work. Okay. I just moved to Germany as a visiting researcher last week in Dresden. So I'm gonna start working on some new project, but yeah, AIST is more like industrial side, so they're trying to apply thermoelectrics to the industry, and probably I can do more scientific stuff in the Max Planck Institute. That's my plan for like a couple more years ahead. It's kind of not responsive. So he explained a lot of the fundamental things. So I think I can skip some of them. But my institute is called Global Zero Emission Research Center. So we are more focusing on wasted heat recovery from electrical plant, like power generation plant or some car engine, to improve the energy efficiency. And yeah, some people are more interested in like wearables, IoTs, which can be also pretty important for the thermoelectric applications. Yeah, so as he explained, ZT is very popular index for thermoelectrics, and the difficult point is low thermal conductivity with very high power factor or high electrical conductivity. That's a simple idea. And our group is working on like nano inclusions for high performance materials like lead telluride or bismuth telluride as well. Yeah, they can reach up to like ZT of 2 or somewhere around there. And also, we also make thermoelectric modules for like high performance materials to achieve high energy conversion efficiency. And this one is cascaded, like layered structure with bismuth telluride and lead telluride. And module efficiency is 12%, which is kind of pretty high compared to commercial materials, commercial modules. So, those are the AIST project. And currently, this is probably more like chemistry project, but today's topic is about Half-Heusler. This is the family of the material. And Half-Heusler is pretty useful for like various applications, semiconductors like magnetic materials, superconductivity, and topological insulator. And for thermoelectric applications, we prefer these high mechanical properties and high power factor, and we can choose a lot of elements from the periodic table. That's also a good point. But the problem is really high thermal conductivity. We want to reduce it by, so people usually use alloying or non-structuring to reduce the thermal conductivity. And this is like typical high performance, high Half-Heusler materials. Like the combination of 3 elements, basically 1-1-1, like niobium cobalt tin or hafnium cobalt antimonite or something like that. ZT can reach up to around 1, which is not that high, but still the mechanical property is really good. And yeah, you can, if you think about some like hard situation like vibrations or something like that. And yeah, allele valence substitution is used to tune the carrier concentration, and isovalence substitution is usually used for lowering lattice thermal conductivity. But I think one problem is you don't have many choices for like alloying or putting some elements for the substitution, because if you choose this row, we only have you can only change the zirconium to titanium or hafnium. Yes, that is effective, but sometimes you change the grain boundary situations, or you can have a phase separation in the matrix phases. Recently people found that this double Half-Heuslers, which is coming from double perovskite, so twice the chemical equation, and you can have a larger unit cell if you have an ordered structure. So the ternary Half-Heuslers, conventional Half-Heuslers, zirconium nickel tin is 18 electron balanced. So this is 18 electrons with these 3 elements. But if you think about the defective Half-Heuslers like zircon nickel indium and zircon nickel antimony, this is 17 and 19. If you mix these two, you can design the double Half-Heusler to sustain the 18 electron balance with semiconducting behavior. These both end members are not stable as the single phase, so you have to mix it to have a single phase. That's the interesting idea, because it's not just alloying. And more than hundreds of double Half-Heuslers are predicted to be stable from DFT, and you can this can be a new platform to investigate the new compositions. And one benefit to make this material, this compound, is if it has an ordered structure, like larger unit cell, the phonon velocity can be lower, so that you can have lower thermal conductivity. Like crystallographic reason to have lower thermal conductivity, because you kind of like holding the brilliant zone, and you have more optical branches, and the phonon velocity goes down as you have larger unit cell. So if you can realize the ordered structure for double Half-Heusler, it would be nice to improve the properties. And this is a previous, there are some report about double Half-Heuslers, and so these people are trying to make double Half-Heusler based on this titanium cobalt antimony. So here the cobalt is just split into the iron and the nickel. So these two, each of them are not stable, but if you make a double Half-Heusler composition, you can get the pure compounds. And ZT is still not that high, but the lattice thermal conductivity is quite low compared to parent ternary phase or general Half-Heusler structures. So it works. So people are still trying to improve the performance, but yeah, idea itself is kind of interesting. So I try to expand this to a triple Half-Heusler. So idea is we just had a 17 to 19, but this time 17 plus 20 electrons can be mixed into 2-to-1 ratio, so that achieved an 18 electron balance. So in this case, scandium nickel antimony Half-Heusler. Scandium position is split into magnesium and vanadium, and if you mix 1-to-2 ratio, you can design the triple Half-Heusler composition. So the nickel and antimony now it's 3. So if this compound has ordered unit cell, you can have even larger unit cell, and you can get the low thermal conductivity again. So it might be worth trying it to synthesize it. And so experimental synthesis is pretty straightforward. Just weigh the elements and arc melt all samples together, or sometimes remove the magnesium and add it later, because magnesium just evaporates everywhere. And formula to mix them and homogenize it together, and we use SPS or hot press at higher temperature, like 600 C, 800 C, to get this kind of pellets. So this is a polycrystalline sample. So this is XRD, and as we discussed, probably these peaks are clean enough. We don't see any impurity peaks, and I believe that these has a single phase. But sometimes you lose some magnesium and get some nickel antimony impurities, so you have to think about the synthesis route as well. And also, the other reason I believe they have this composition is you can see that the lattice constant is linearly changing with vanadium content. So this is end member compositions, magnesium 1-1-1 compositions. You can see the density and lattice parameter changes linearly. I think this is enough to believe in we have a single phase. And SEM with EDS map is pretty clean. But sometimes just ternary Half-Heusler compounds is difficult to get the pure phase, but I think this is homogeneous enough. And it kind of low magnification for this picture, but if you really look closer, I don't see many problems of impurities or secondary phases. And yeah, from the definition, I think I would like to mention that the terminology difference between just the disordered alloy Half-Heusler or double triple. So conventional Half-Heusler also makes alloying on one side. So it looks like a double Half-Heusler composition, but it's actually different, because if you look at the phase diagram, the both endo members are stable, and just if you go higher temperature, it's just mixed as a alloyed Half-Heusler and just Half-Heusler phase. But actually, at 0 Kelvin, it should be a phase separation or something, right? But on the other hand, like double or triple Half-Heuslers, endo members are not stable as a single phase, so there is no single phase region, probably. Probably yes, but probably not. But the double Half-Heusler phase itself is a single phase even at 0 K, and they have the different crystal structure and ordered phase. Actually, we didn't see the ordered structure here. This is just a Half-Heusler phase, so it's completely disordered on magnesium vanadium side. But this phase diagram definition, just alloyed conventional ternary Half-Heuslers are different from this kind of single phase to disordered structure. So that's the crystallographic definition and material scientific definition of the double Half-Heusler and conventional just alloyed Half-Heuslers. And these are the thermoelectrical properties. Seebeck coefficient is 100, somewhere around 100, which is somewhat low, but it still have a semiconducting behavior, because if you look at the 111 composition magnesium nickel antimony, this is a vanadium zero situation. You only have like 2 or 3 Seebeck coefficient. It's very, very small. And if you deviate from the triple Half-Heusler composition, this is magnesium 2.5. And the sample 3 has a really impurity phase. The Seebeck coefficient just goes really small, like 20. This is like more like metallic. And band gap estimated from this Seebeck peak is 0.1 or 0.2, so kind of small, but still have band gap, small band gap. And electrical conductivity, decent electrical conductivity leads to a power factor of 1 milliwatt per meter Kelvin squared, which also not super high, but decent, I would say. Like this material can be 3 or 4, so not reaching to the best performance material, but not just disappointing result, I guess. And more interesting, thermal conductivity is much lower as we expected. Actually, this is completely disordered structure, so we don't think this is because of the expansion of the unit cell, probably just because of the disorder in magnesium vanadium side. But lattice thermal conductivity goes to almost like 2.5, which is much smaller than like parent material. Scandium nickel antimony is more like 10, 12. And this is a double Half-Heusler composition reaching to 3 or 4 at higher temperature. But it's pretty flat because it's alloyed, disordered. And just staying at the 2 or 3 is pretty low as a Half-Heusler compositions. And yeah, it's just compared to other well-known conventional Half-Heuslers, they have like 10 to 20 at room temperature and somewhere around 8 at the higher temperature. But this is our result for triple Half-Heusler, so it looks very small thermal conductivity. And ZT is just still less than 0.2, so not very good because the highest one is like 2 or 2.5. But also, if you compare to other double Half-Heuslers or scandium nickel antimony, it's also higher. And if you take a look at the example of conventional ternaries, this is like just one single phase. It didn't put the alloying or dopant, and they just changed the composition, slightly changed the composition by to tune the carrier concentration or something. GT can be much higher, like 5 times higher. So if this is just we can think it as a parent composition again, and if you tune the composition a little bit more, there is a potential to have a much higher thermal performance, I guess. Yeah, so this is summary. I think this is the first report of synthesizing triple Half-Heuslers, even though this is completely disordered. I think the reduced lattice thermal conductivity is interesting to further investigate a little bit more. And yeah, we have decent Seebeck coefficient and power factor. And I think this result can expand the potential combinations of elements to design Half-Heusler compositions. And yeah, that would be great if you have any ideas to work with this guy, because I just started this project from this year, kind of. So it's still a baby project. So I think we can think about other possible like analysis is etc. Yeah, this is acknowledgement. This is a Japanese group, and yeah, mostly technical stuff. No one students. Yeah, I just took a picture of Dresden. Yeah, that's it. Thank you. Thank you very much.
Kazu, thank you very much for a great talking. First of all, I would like to ask you that the efficiency of the thermoelectric module that you made is at 12% is quite good values actually. Is that for cooling, right? Or for power generation?
I think it's for power generation.
But I didn't understand how the mechanism of this cascade module can be used for power generation. Do you have an idea?
Yeah, I mean, yeah, this is not a practical module. It's just for lab scale, like.
No, I'm saying that like you have to apply the heat sources on the one side.
Yeah.
So how the heat can be reached the down side?
Yeah, I think just heat coming from the top and just goes to the bottom, and the temperature goes down as you go down, right?
Yeah, but there is a barrier between these two legs. That's make me a little confusing. Yeah.
Yeah, this is not the like complete barrier. I think it's just a conducting layer to connect these two.
Why then you use the cascade model? So why is
because this guy is laterally. This is like good for high temperature, but I think lower temperature for business to cover the lowest part, so that you can have a high average CT for entire temperature range.
I see. So okay.
Because if you use laterite for like just 300 Kelvin, it's going to be really small.
So you think that the temperature goes into the like the lower?
Yeah, as you go down, go through, the temperature goes down. Right?
Okay.
So probably, yeah, some temperature profile can be estimated from the.
But they are going to produce a different voltage from the top and bottom. How are you going to balance?
Yeah, I think they just use
some electronic circuits. I see. Okay, thank you very much. And for the second question, I will ask you. So you said that you made like a triple Half-Heusler, which is actually basically start from the N-type, P-type mixing of the N-type and P-type, right? So how do you know that how much we have to put N-type or P-type to balance? Because one of them have like a P-type conduction, the other one N-type. So
yeah, I think so.
You destroy the
so we are just trying to count up the electrons. As I mentioned, probably this. Usually, they try to aim for 18 electrons count. So just ternary compounds. So. Like magnesium is just 1 electron down, right? And vanadium is 2 electron up. So if you combine 1:2 ratio, it's going to be closer to 18, and it should have intrinsic semiconducting behavior. But this time it's P-type because probably slight magnesium vacancies formation or something.
Yeah, that's interesting because the Seebeck coefficient is quite high. That shows that like a hole is dominated most likely. Yeah. So that shows that the P-type should be dominated in this Half-Heusler, or
I think the most favorable
when we mix it should be like higher content of the P-type in this, or no?
I'm not sure. It's kind of difficult to control the exact amount of magnesium, so maybe it affects somehow. But we are actually trying to balance this changing the ratio and can get to N-type or not. The N transition might be interesting to see.
Okay, so thank you very much, Kazu, again for this nice talk.